Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 32, rates and orders of reactions, part 5, horizontal and vertical shifts of exponential functions. So we are still describing first order kinetics, but today we're going to learn how to perform vertical and horizontal shifts of exponential functions and apply these shifts to describe drug release and delayed drug release from dosage forms. Now, vertical shifts can be brought about by adding or subtracting a constant number to the function, whereas horizontal shifts of exponential functions can take place by adding or subtracting a constant number to the input variable of the exponential function. That would be x or t. So if the parent function is y equals to 4 times e to the negative 0.2x, the vertical upward shift would be with a plus 1 into the function, whereas the vertical downward shift by 1 unit would be with a minus 1 into the function. Now, the left shifted function by 1 unit would be x plus 1 into the input variable, and the right shifted function by 1 unit would be x minus 1 into the input variable. So let us plot these functions to see how they look like. So here I have my parent equation, and the green line is the upward shift by 1 unit. The red line is the downward shift by 1 unit. That's why I have negative 1 here, or minus 1. And the bottom panel shows the horizontal shifts. So the thick line here is the parent function, and the green line is the left shifted function. That's why in the input variable I have x plus 1, and here in the input variable I have x minus 1, and this is the right shifted function by 1 unit. Okay, now it is important to understand that these vertical and horizontal shifts do not affect the drug release profile. So dCdt and of course K and T half are all remaining untouched. Okay, so these dosage forms will all display the same release profile. It just happened that if you have a delayed release, if it starts late, it will finish a little bit late as well. Okay, now let us apply these techniques and try to come up with an equation that simulates drug accumulation or drug release data. So here I have a control release product, and it releases a drug at constant time intervals, as you can see here. And in this table, this is the concentration released, okay, not the concentration remaining. So if you try to plot a length c versus t to determine from the slope the rate release constant of this drug, you're not going to be successful because it won't be a line. Because this is not the concentration of the drug remaining, this is the concentration of the drug released. So how can we come up with an equation that simulates drug accumulation? So we're going to demonstrate how we can do that by reflecting exponential functions into the x and y axis and by vertically shifting those functions. So let's take a look. So here we are. So I'm going to start with the parent function c equals to a times e to the kt. So I have a positive exponent there, and this a is equal to c0, all right? So here I have the blue line. This is the e to the kt. So this is, let's say, c is equal to c0 e to the kt. If I want to generate a negative sign in the exponent, all I have to do is to reflect this curve into the y-axis. So this curve here is equal to c is equal to c0 e to the negative kt. And here I've plotted only the positive part for positive time. So again, this is c equals to c0 e to the negative kt. Okay, if I want to generate a negative sign into the coefficient, so if I'm going to generate a negative, so this is going to be c equals to negative c0 e to the minus kt, all I have to do is reflect this curve into the x-axis. And here is what I have. And now, if I want to shift this by c0, okay, I just have to add. So c is going to be this one. So c is going to be c0 minus c0 e to the minus kt. This is the curve, and this is the curve here This curve here describes drug accumulation. All right. So this is what we shown over here. So this is now my curve, C0 times 1 minus e to the minus kt. This curve is able to simulate drug accumulation or drug release into biological media. Now, in our case, remember that the highest concentration was 100. So that's why I've replaced C0 here with 100. Now, from this equation now, you can use the data in the table and determine K. You can use any of the time points. So here I am. I'm using, in this case, C released was 18.1 for the time 1 hour. And I have rearranged this equation and solved for K, okay? And now I'm substituting the values, 18.1 for 1 hour, okay? And the answer here is 0.2 per hour. So this is the drug release rate constant. Now I have to also tell you that obviously this is a method that is already known that it's first order kinetics and is a perfect fit. Otherwise you would have to use the best fit equation to figure out the K. And that can be done by a non-linear regression analysis, which it is not in our scope in this lecture to demonstrate that method using a spreadsheet software, okay? And this is time for you to practice. In this exercise, I'm asking you to model the delayed release from a control release dosage form, and in this case you're going to have to perform horizontal shifts, not vertical shifts. These are the answers for D and E, and these are how the profile, the drug release profile, should look like. And at this point we have reached the end of this lecture. I would like to thank you very much for your attention. Until next time.